Both? Okay. A little bit of both. Alright, so let's check a textbook first, and then let's kind of take a temperature probe on where we are. After that, we're going to talk about Le Chatelier's, which, who remembers Le Chatelier's principle in honors chem? Shift left, shift right, no shift? Anything like that ring a bell? Le Chatelier's. Okay, so I got 4 people on board. Okay, so that's what we're reviewing it today and tomorrow, so you're good. Alright, so in the first example, they gave you initial information only for the 2 reactants. For the equilibrium, and then you had to solve for the other. So they gave you the KP, right? So you had to have a question? Already? What's up?
Well, it was like, so that wasn't the answer that I got first, but the textbook said it was different. So then I
To
to
atmospheres.
and then I got the right one.
So the textbook was just taking it specifically, because they have to establish an answer, right? So they went to atmospheres. If you were doing an example for me or for AP exams and they don't specify a unit that's to be used in the KP expression, you can use that example, you can use the units given, but if it specifies a unit, then you need to convert to that. So, yes.
Okay, so why would you stop there? Because don't you need to like do extra C's with the...
Hold on, not have more here, but I was sort of okay, so you have equilibrium values, you have your partial pressure of products over partial pressures of reactants, you have a squared and squared involved as well. Since you're solving for x, you're multiplying them by the KP value itself. X squared is then equal to this big number. Solving for x gives you 6,461 torr. Give me a thumbs up if you made it that far. Alright, so mostly thumbs up, okay? And then specifically, what was the partial pressure of nitrogen, or NOBR? And this, specifically, that would be what? That times 2, right? I didn't write it down, sorry guys. Okay, so this is the process though. Clear on the process? You're just solving for one equilibrium value. Yeah. Because this specifically, when you're making, no, actually, lies. This should be right. Because specifically, I solved for a value, like a singular value of x. Like I just called this overall quantity x, specifically in mind. You guys with me? So since I solved for that value itself, it wasn't like I was minusing x and adding 2x. That should be the value at equilibrium. Point blank. There's no multiply by 2, there's no squares. You good? Okay. So this is P and OBR. Now, if you had a polarized box and you were solving for x separately, that would be a single entity. So therefore, this would have been equivalent to 2x, so you would have had to multiply by 2 at the end, but that just called it x. You could have called it cat and solved for cat, and you could have done that. Okay. All right. So for the next one, you had. I wanted you guys to write down the process so you could understand that talking through the process, as well as doing it like full out. You can talk through it first and make sure you're clear on how to get to the end, and then also make sure that you're going to be able to plug it in mathematically. Because you guys are strong in your math, so understanding like you can talk through it too is also valuable. So they gave you initial conditions of grams, and liters, basically for everything. So to find the equilibrium constant. So you did have to take your grams to moles to molarity, so just dividing by liters. Okay. When you plug in those molarities into the 2 reactants, that's all that were given to you at first, and then it says at equilibrium, the flask contains some amount of 45. I wrote down H2 and I2, but it goes, it's methanol. You guys, no, that's 45. Okay, there we go. I'm looking at 46. So you have a specific value here, here, and here, and since your job is to find the overall equilibrium constant, you did have to take these individually, minus 1x plus 2x, because you did make that, so that's how you know you're adding it to the product side. So then once you have number minus x and then number minus x, you'll be plugging these into your 2 reactants, this value squared into your product, and then you'll plug in those values for KEQ or KC. KEQ is just a cheap way of saying anything. Okay? All right, so who struggled on, was it Yeah, 49. Okay, so in essence, the value of K can be achieved in many situations. So we've dealt with partial pressure situations, we've dealt with concentration situations. Then this was one where you had a solid dissociating. So you had silver sulfate dissociating to silver ion and sulfate ion. This is called a solubility equilibrium. So we're taking a solid and we're seeing how soluble it is by seeing how many ions are produced in its dissociations, like in aqueous solution. So this would be like a precipitate dissolving just a little bit. So this is what we're going to be learning about more next week. But the scenarios are all just scenario based, but the math is all the same. So that's why we just make sure we're clear on how to do ice boxes, and then we can do it for anything. Okay. So what's the first thing you guys have to do? Calculate your. So you can first calculate K constant though. You have to find the molarities and then do what? Plug them in, right? And then you're going to compare K and Q. Good. So that's your thought process, and if you know you can achieve that, then you're good to go, because that's going to get you to your final answer of which way it's going to shift. So you're given the K value, it's pretty small. You're given these two ions, and this is solid, so you're excluding the solid from the K expression. So concentration of silver ion will be squared, sulfate will just be raised to the first power, and you're answering basically which way will it proceed, left or right. So given 6.55 grams of silver sulfate, you can find a molar mass, you get moles, you divide by liters, you should get a molarity of 0.0140047. So you can get your molarity. Thumbs up if you understand how we're getting molarity here. Okay, so that's for the silver sulfate. What's weird is that truly that solid is not dissolving in aqueous form. Not very much anything. So what you have to see is that this is like a theoretical molarity of sulfate, and I wanted to see what you could do before I taught you KSPs. But that's technically like how much of this should be dissolving. But what you'll notice is that this dissolves in a what ratio with the ions? 1 to 2 with silver, but 1 to 1 with sulfate. So this should be how much sulfate is in solution, because it's a 1-to-1 ratio with itself. But what should we do to figure out how much silver is in solution? Right, multiply this number by 2, because it's gonna dissociate twice the rate as the other. So I kind of just wrote that down here so you guys could see that relationship, 2-to-1 ratio, 1-to-1 ratio. So then you'll plug those concentration values into your Q, because it's basically saying, like, here's what I have in solution. Am I at equilibrium, yea or nay? So when you plug those values in, you get 1.0 times, or 1.1 times 10 to the negative fifth. So how does that compare to the K value they gave you? Higher or lower? Here's your K value if you don't have it on your paper. Okay, so it's kind of weak, right? So it's approximately at equilibrium, right? Is it at equilibrium? Approximately, right. Okay, so no more solid forms, no more ions form. It's going to be an equal forward, equal reverse reaction. So reverse and forward and reverse occur at the same rate. Yeah. Yeah, that's a saturated. That's a perfect. Thank you for bringing that up. This is a saturated solution because when you have a solution and you have ions being formed, you have your solid here, and you have your ions being produced, and precipitate is forming in equal rates. So this is rate forward, this is rate reverse. But it's a constant dynamic saturated solution too. If you add more ions, more precipitate will form. If you take away solid precipitate, more ions will form, because it's going to come in equilibrium with its saturation point. Good. Okay, so the last one was an acid problem though. So we have, what acid is this? Acetic acid, right? So it was aqueous, we had liquid water. Is that included in our equilibrium? No. And then 2 aqueous ions. So this is a weak acid, right? What is so true, or what's a fun fact about a weak acid? How does it dissociate? Okay, so it doesn't dissociate? isn't completely dissociated. So it still dissociates to some extent. So it doesn't completely, like nearly, maybe 1 or 2% of it dissociates, which is why we have such a small K value, right? So weak acids have a low rate of dissociation, which is why it has such a small K value. So what we did want to find out though was the concentrations at equilibrium. You were given the initial concentration of acetic acid, and then omitting the two products, you just put zeros. Who did minus X plus X plus X? Okay, so we see the small K value. We notice that we're going to get down to eventually a quadratic. So when you plug in your K expression value, or K expression, kind of just have to get rid of this now. Okay, so when you have your K expression here, products of reactants, you plug in X and X, and then the 0.2 minus X, noticing that's a small value, I'm going to go ahead and try to make the math easy and start to neglect that. So then you get X squared over 0.12 or 0.21. And so mathematically, how are you guys solving this? Multiply by the denominator and square root. So then after you get your value, the 1.94 times 10 to the negative third, you still have to verify you're able to neglect X. So you divide it by the smallest number you would have subtracted from. And that gives you your ability to, because it is smaller than 5. Yeah.
So what's the number that's I feel like 10 to the negative is small, but like too small, it's like negative 30.
So a lot of times if you have 1 times 10 to the negative third, not molar, for your K value, I'm pretty suspicious from that point on, but it really does depend on your initial concentrations. Like this is a 0.2 number. If I had like a 10 molar solution and I have a small K value, that would work a little differently than if I had a 0.0001 molar solution compared to a small K value. Because a 0.001 solution, a small difference in X makes a big difference in percent. So that's why you have to be aware, but then always double check at the end. Okay, so yeah, but usually if your K value is like less than 0.001, then it's probably small. Okay, all right. So major questions right there now. Yeah.
So you compare Q and K with one of those two.
You compare Q and K if all the initial conditions are values, like true values, not non-zero. Or sorry, if they are non-zero values, and that can give you an indication of if you already have two products or if you already have two reactants, you then need zero. Right? That one was one where it gave you as solid values, which we couldn't utilize because it was not included in equilibrium. So we had to go find our initials for the two ions. Okay, we'll work with K scale a lot more. I want to see which case you do first. Okay, this is a quick check to see where you are. Please do not fret about this. This is something I want you to try just for me. Just for me, okay? So, yes, you do need a calculator, okay? This is a quick check. You guys that did not call this a quiz. I have two quick checks. I have two quick checks. And this is the one I want you to do first. This one's harder. You can write on this. Feel free to write on this. Do not talk to anybody. Do not talk to a soul. I want you to see what you can do because it's only you and me. We're going to see this. Make sure everybody gets one of these, please. 1, 2, 3, 4. Pass all the back to you. Yes, you will need your calculator. Make sure you can calculate it. Just give this a whirl. I'm a video for my folks viewing at home. Okay, so the ones that you are capable of doing, check. You can do this one. Check. You can do this one. You can do this one. You'll be able to do this one next week. Okay? You will be able to do this one in January. So this is was this December? Okay, December, mid-December. Okay, January, and this other one is tomorrow. Okay, so Le Chatelier's principal tomorrow. Like January. Yeah. Huh? It's Friday. So not tomorrow Friday, but I'm gonna. It's on my website though. Yeah. So I try to tell you where I can. Oh my gosh, there's so much on this website. So whatever day that falls on, we're up. Like this is tomorrow, Friday, Monday, Tuesday, Wednesday, Thursday, Friday. Yeah, next Friday. So. All right, finish that last equation. Finish the last equation. Moving on to Alright, put the markers down, people. Put the markers down. Okay, halfway close your computer so I know you're with me. I think that this should take us no more than 10 minutes to talk about Gibbs and equilibrium again. Remember Gibbs? Yeah, you remember how it relates to equilibrium? Do you remember the equation? Delta G? Alright, good try. It's got to relate to equilibrium. So, put your delta G is equal to no. Okay, so alright guys, with me. Shh. Halfway close your computers. We're taking notes real fast, okay? Now some of this is like 90% of this is very, very familiar. There's just one extra piece that I need to verify that you're clear with. So we know there is a relationship between K and Gibbs. Gibbs is telling us information about what? Is the reaction thermodynamically favorable? In the which direction have we always considered? Forward direction. So we know that's what Gibbs has always been giving us information about. So negative delta G means it's favorable in the forward direction. Positive delta G means it's favorable in the reverse direction. Or we just always said not thermodynamically favorable, but in our heads we're like it's in the forward direction. Okay. So now we're making these connections between forward and reverse. K data, like K greater than 1, tells us that it's
favorable towards
wrong. Okay, so products are favored, but another way to state that is like you were just saying. Favorable in the forward direction, right? Which is the way the products are, right? That's where the products are, they're the forward direction. So K greater than 1 should tell you information about delta G. and delta G should tell you information on K. They do have a relationship. We know there is an equation that relates them. It's on your reference table. But let's talk about like the theory or the concept behind this connection. So, what does Gibbs really stand for again? The full title of it? Free energy. So Gibbs free energy. So is a reaction more stable when you have more free energy in the reaction, or less free energy in the reaction? Less, right? Less energy overall, like kinetic energy and Gibbs free energy in this case, in the products means that they're more stable. So we always want to have a reaction that is releasing all this free energy to the universe. So it will do that naturally. It will flow in the direction for the reverse, whichever one that's going to release most free energy to the universe. That's the way it will always work. So it's just like a ball rolling down a hill. It will go to the point where it's minimum potential energy, which is going to be releasing all this free energy. So that's just an example to relate it to. So we remember this. Write down what you need to. Some of this is review. Most of this is review. So, just as a side note, that quick check we just did, just as teachers like to know where you are, right? How in the world am I supposed to know where you are? I have to ask you. You give me an honest response like 1 to 10. I can say, hey, here's a quiz. Let's check where you are. That's more stressful on you mentally and physically, I think. I can ask for you to write me a little reflection like, hey, I feel really good about this, and I don't feel so great about this, and I have no idea what we're doing with this. I don't have time to read all the responses to that every single time, but I will do that occasionally. So a lot of times if I'm gonna quiz you, I want to quiz you for a grade. But I gave you the FRQ, and I did not think it would be fair to give you a grade for that because that was a lot more in depth than I initially intended. I had the other quiz ready to go, like I got it, but I wanted to see how you could do on FRQ because then that would give you more support in your test, right? So guessing a question just like you saw on a problem set, like one single statement, find K, doesn't necessarily prepare you for your test because as you know, free responses are like A through Z. So you've got to be able to apply A to B, B to C, and C to D. So that's why I want to see where you were there. And I write them down just for my information so I can kind of see where we need to go. Did going over that help a lot? It kind of either solidified knowledge or gave you some perspective to see where you can focus your efforts. And that's really all I ever want to do is give you feedback, not in a stressful way, because the test is stressful. Yeah.
Just a question, the FRQ you just said, that did we do an increase from there, or was that opposite?
So that one was only dealing with graphical analysis and concentrations at equilibrium Q. As we learn a little bit more with KSP, it's going to ask us a bit more about precipitations and like saturated, supersaturated, unsaturated, and then eventually Kas and Kbs can start talking about pHs. So like as we learn more, there's more review pieces that come in. This one I could ask about like delta G, technically, which is why we're doing this right now. So I would say that's a medium. Yeah. All right. So let me show you this graph first. So this graph right here is called a free energy graph. And what we want is lowest free energy in the system overall at the end of the reaction. So the reactants might start with high free energy or high potential energy, and then the product's made with lower. That has met the goal of delivering free energy to the universe. And so this would be a favorable reaction in the forward direction. So we would know two things about a graph like this. We would know delta G is what? Negative, and we know we would know K is what? Greater than 1, right? Because products are favored here. A graph like this would give me information that says what? Delta G is positive and K is less than 1. So we would say the reverse reaction would be favorable. Okay, so we don't see these very often, but if you ever did see a graph where it was a Gibbs free energy graph, it would kind of have that U shape. And that's just called a free energy curve or Gibbs curve. You guys good with that? This ball example is just like relating it to everyday life. It's not that important. Can I move on? Yeah. All right. So, do you guys have your reference tables close? Let's look at the delta G equations and let's look at the K equations. Kind of different. That piece is just talk about all the time. I'm gonna look on the front of the bus. So everybody look down at the lower right-hand side. Do you see the delta G's? We see delta G's equal to delta H minus T delta S. Negative RC on the K. Eventually we see E, which is energy, which is electric chemical energy, electricity. So that's what we're gonna be referencing. Notice the equation I have on the board right here. Do you see that one? Do you see that one? Where's it at? Oh, you guys see that one? Okay, sorry. Do you see it on the reference table? No, okay. So the idea is that we can represent, quick review. What's the little knot mean? Standard conditions between concentration is 1 molar, pressure is 1 atmosphere, and temperature is 25 degrees Celsius. Okay, so we know that this little knot means standard conditions. But is everything always at standard conditions? No. Okay, so we assume that initially, like this is a comparison data point. Like if I had a really, really negative delta G at standard conditions and a really minorly negative delta G at standard conditions, I could then compare those two values and say, oh, one's more thermodynamically favorable than the other. So we have the standard conditions to compare everything across lines. But in equilibrium, do we always have 1 molar conditions? No. So a lot of times we'll have just a delta G for that, not with a knot. So that's why there's a relationship between here. You'll notice that then I also have Q in here, because at equilibrium, we have K, but at non-equilibrium conditions, we have Q. Because this is always the one we compare to equilibrium and say, hey, how do I get to equilibrium? So this is not an equation you'll use very often, but it's a relationship to the one that is on your paper, okay? So we know that we can always figure out if we're going towards reactants or products by looking at what? By looking at G? Are we, well, this is based on what you know. I can always look at two values and then from there make a comparison and compare K and Q, right? So generally we're going to do K versus Q, and that's going to give us information how we're going to proceed left or proceed right towards reactants or towards products. But given G, we know that which direction is going to give us the information, or sorry, which direction is thermodynamically favorable, which would give us information which would be the favorable direction to flow in. So we know we have to read the question carefully to just decide if it's talking about thermodynamics or if it's talking about Q versus K. Okay, and then this was a fact. When did you guys learn this? That delta G was equal to 0 at equilibrium. We learned this in, was it thermochem? Yeah, it was on the thermochem test, right? So we had to understand that delta G negative meant flow forward very thermodynamically favorably. Delta G positive meant flow the opposite direction. But then we had this one scenario where we actually had physical equilibrium. So at physical equilibrium, which on the thermochem test it was like melting, I think. It was saying, hey, I'm at the melting point, and they had an equilibrium arrow. We should know that delta G is 0. It's not favorable in the forward or the reverse direction once it's at equilibrium. Okay, but we always say reaction proceeds to the point where delta G is equal to 0. Notice I did not put a not there. Right? So this is conditions, any conditions given for a scenario, not just 1 molar and 1 atmosphere and temperature is 25. So what we do is that equation I had at the very, very beginning, I can compare the fact that at equilibrium, delta G is equal to 0, but once I'm at equilibrium, Q should therefore equal K, because that is the situation at equilibrium. So what I do is I plug in plus RT on the Q. I'm plugging in data points here. So if this is 0 and this is K, how do I rearrange this equation? Subtract RT ln of K on both sides. And what do I get? G naught equals negative RT ln K. Right? So that's the one we've been using, but those were given information. That was given standard conditions, delta G, and the fact that we were already at equilibrium, so it said solve for the K value or vice versa. So just understand there is a relationship to pre-equilibrium, but this is the one that we are eventually going to be using most commonly. That's about it. Okay? I'm going to verify that's about it, but hold on. Give me a thumbs up when you get here. Okay. The only statement that was a little bit of a refresher was that delta G is approaching zero equilibrium. Oh, and then this is, I'm going to go back to this in a second. This is just a data chart to show you those relationships. So a very positive delta G means what? So not thermodynamically favorable in the forward direction. And then what does K show us here? Reactants are favored. So they should agree with each other, right? So this shows reactants are favored. And this essentially shows the reverse direction is favored, which is why we're saying thermodynamically not in the forward direction. And then vice versa, negative delta G and a very high K value. Know those correlations. Are we clear? Okay. And I think, I'm not going to solve this. We've already done this like in our lab. But given the fact that you've had data, like say you have a whole table of G values for like H2O, H2, and O2. Actually, what would these two data points be? 0 because of free for delta G, free elements are 0 for their free energy. So we have a number here. How would you solve this? So how would you solve for the delta G reaction? Nope, don't have information for that. Given these data points, like given a table of values for delta G, how would I solve for delta G reaction? Products minus reactants, very good. Okay, so delta G products minus delta G reactants, right? So I'd be plugging in what here? Zeros, right? Because these are both free elements, minus how many? 2 times number, right? Because there's 2 waters. So 2 times number. I like to plug in fake stuff, sorry guys. So this is going to be a negative number, right? 0 minus this, assuming it's positive. Yeah. No, because in delta, remember in all of our delta H, delta S's, and delta H, S, and delta G tables, they always gave us specific values that would be per state of matter. So like this might be gaseous, it might be liquid. Doesn't matter in this, like this is liquid in this case, so it would give us liquid data points. So 1 second. So we'd be solving for delta G of the entire reaction. And then once we solve for that delta G, how would I solve for K? Negative RT ln of K, because I'm still solving for the equilibrium constant for this reaction up here. And that would give me this value once I divided by what? What's R? 8.314 joules per mole K. And this is probably in what? Kilojoules, because that's how I defined them over here. So if this was in kilojoules, I'd need to do what with this? Convert it to joules. So how many joules are in a kilojoule? 1,000, so it'd be 1,000 times greater, right? What would be the T here? But what would it be? 298, because that's what standard conditions of temperature are. And then once I divide by that on both sides, I have ln of K is equal to big number. How do you get rid of ln? E to the ln of K. Okay? And then you can solve. Now, if this delta G is negative, what should the K value be? Higher. If this delta G is negative, K value should be high. Okay. Right. So do you see now that we can connect equilibrium to K very easily? I did not do that on your thermodynamics test. Quick questions? Yeah. Yes, it would have to give you all the data points as, sometimes not always, right? These typing out superscripts and subscripts, or we got them all in here across here. Yeah, these would all have to be at standard conditions.
Is there a way to do?
You have to use the other equation, and you have to give all the delta G's for all the non-standard condition ones. So probably not. Question over here? No? Okay. All right, so we're not going to quite get to this today. So I'm going to pull up the NMSI, the one that you guys read the other day. And you are going to, who's already approached some of 1 through 8? Okay. Questions on those, I'll come around to you. And then I do want you guys to read this one last page. If you have yours in front of you, feel free to pull that. So the last page is on Le Chatelier's, and this is to prepare you for tomorrow. So if I pull it up here, notice that a lot of examples, like tons of examples in here. All right, so this is your part of your homework is to read Le Chatelier Intro on an SMI. Start reading first if you have in front of you, outline if you need to. I'm going to try to show you a video at the end of class too. You look at your laptops right now though, we're not going to do that. It was easier asking. Guys, if you want to copy the easier quiz, I'm not going to give this right now. I'm not going to use class time. I'll just pass it out.
This is what you're looking for whenever you
This one is easy, but I got what I needed, so I'll just rush you more than I need to. You got more. I'll give you Right. Yeah. Sorry. These are writing so fast.
this was yeah, it wasn't yesterday.
Sorry. How do I do this every time? Just for today.
You must flat said that. She was like, you already even marked that. Okay.
She probably